cool. Yeah. It is smoke, it is incense. It is sandalwood. Because it's Incense Wednesday. Alright, let's go through the ODP. So I don't think it's running yet. I think it'll start in a few minutes. But let's go through this. So 214, you're going to make a function that hashes a string, returns an integer between 0 and 30. Almost exactly the same behavior as ODP 213 with one key difference. Your hash function takes a second argument, which is a probe number. It's the number of attempts that you've made on this hash function. So call hash with a string and an integer, which we call the probe. And here's some samples of what you should get back. If the probe is 0, you should get back the same values that you were getting before. But with a probe of 1, you will get different values. So our hash function is slightly more complex. So same deal. Add up the ASCII codes of each character in your string. So go up to string length -1, so you get every character. Don't worry about the null terminator. Add that up, and then to that sum, add the square of the probe, and then reduce all of that mod 31. Alright, cool. 214 is working. Yay, I did it right. So I don't know what happened yesterday. Some kind of glitch. But yeah, it's out there. I don't even know how I have this thing working anymore. It's kind of miraculous. But it works. I need to write something to automate the creation of ODPs. That's on my deeper list. Alright, so hash function for 214, exactly the same as 213, except before you reduce mod 31, add the square of this second argument, which is an integer, the probe number. And the effect of this is pretty straightforward. With a probe of 1, your hash value changes by 1. So it goes from a 4 to a 5. With a probe of 2, your hash value will change by the square of 2, 4. So it goes from a 4 to an 8. With a probe of 3, your hash value will change by 9. So it goes from 4 to 13. With a probe of 10, your hash value will change by 13. Sorry, by 100. So it goes from 4 to 104, which if you reduce mod 31 gets you to 11. Alright, so that's the basic setup. So why are we probing? What's the deal with this? The deal is the following. We've got our familiar hash table. It's got various spots we can store things. And you have some key, and you hash it, and brings it to some location. that location's in use, we need to find another place to store it. So we rehash with a different probe, and it will give us some new location. We hash with a different probe, it'll give us some other location, and eventually, right, hopefully we find a spot to store it. The hash function does not modify the probe. So in your add function that we saw yesterday, right, we had a little while loop which said while the spot we're trying to use is busy, increment the probe, and then pass that to the hash function. So the hash function just ingests that but doesn't modify it. So let's say that this is the location that our first attempt at a hash, so hashing our key with a probe of 0 brings us right here. So if that spot is in use and we rehash, what's the next spot it's going to try to store our key in? How does it relate to this first spot that we tried? One spot down. So it's going to try this spot right here, one spot below. And if that spot's also occupied, using this probe function from ODP 214, what's the next spot it's going to try? Four spots from the original, you got it. So what's the effect here? If we try to use a spot and that spot is busy, we try the next spot. Because, you know, maybe we just got unlucky, we bumped into a location that somebody else had already used. So we just try the next one. If that one's busy, we've got two spots in a row that are occupied. So maybe we're in the middle of a cluster. Maybe there's a bunch of stuff that's being used here. So let's move down a little bit further. Let's go down 4 spots from the original. If that's also full, you know, maybe we just got unlucky, but maybe there's a big, you know, bottleneck of spots in use here. So let's go even further down, somewhere totally different. All right? So this is something called quadratic probing. It's a fancy word, but it really just means we each attempt we go further down. Right, so with the square. So the probe is basically changing the index of the array. Yes, exactly. It's changing the index in the array at which we are trying to store our key, to be more specific. Right, so this is, you know, you're at the movie theater and you're standing in line for popcorn and the line is busy. And so you like move one spot down and that line is really busy, and so you move another spot down and that's really busy, and so now you go like to a totally different section on the other side of the theater and hope that, you know, there's no congestion over there. So this is moving further and further away each time that we probe. We could also do linear probing. And in linear probing, if this spot's busy, we try the next. If that's busy, we try the next. If that's busy, we try the next. And we just keep trying sequential locations. That's, you know, a little simpler, but if we have a big collection of things here, we're going to go one by one to get out of that, and then eventually get to another one, and that's going to lead to more clustering, right? Every time that we got a collision with any spot in here, the next spot that we're going to use is the first free spot after that cluster. With quadratic probing, right, if we start here or we start here, we're going to go to different locations because we're using the square of the probe. So that's the idea, and those are just two really basic hash functions that use a probe value. But, you know, we can get much fancier than that. we can come up with all kinds of things. When you have squares, right, our first attempt is right after the spot that we really wanted. This one is 4 after, this one is 9 after, this one is 16 after. The distance from that original spot is increasing, but the amount by which that distance increases is also increasing. In other words, here we moved down 1, here we moved down 3 from the previous attempt, here we moved down 5 from the previous attempt, here we moved down 7 and 9, and so on. And so the amount that we're jumping from the location that we just tried that was busy is also increasing. So we're trying to spread out our use of the hash array. If you like, this is the second derivative, right? X squared, 2x, 2. A little calculus thrown in there. All right. So assuming that we had, so any questions on the ODP or on the notion of probing, quadratic probing, why we're doing that? So we talked about adding yesterday, right? We worked through an add algorithm in pretty good detail, and we started talking about searching. And there was this thing we had to keep in mind, which is when we're searching for something, if, well, let's just write it out, because that was kind of where we left off. So we've got a key, we've got a value, we've got an in-use field. So we've got key 1, value 1, key 2, value 2. Let's say this is key 3, value 3. And let's say that hashing key 4 with a first probe takes us right here. And so these are all in use. So that's in use. So we rehash with a probe of 1, and let's say that takes us down here. So we store K4 with value 4, we mark it in use. Okay, so if we want to search, or let's say, you know, I don't know if I called it fetch or get yesterday. I'm going to call it fetch. Let's say we're trying to fetch the value associated with key 4. We're going to hash key 4 with a probe of 0. It's going to take us here. We check the key. Right, we see it's in use, so there is something stored here. We check the key. It's key 2, not key 4. We're not ready to give up and say this is not in the table. We rehash with a probe of 1. That brings us down here. We check the key. Oh, that is in our table, so we return value 4. Now suppose we search for some key K5, and let's say we hash K5 with a probe of 0, and it points us right here. That spot's in use, but the key is not K5, so we rehash. And maybe that points us over here. That spot's in use, but the key is not K5, so we hash again. And maybe that points us right here. It's not in use. Now we can say K5 is not in our table. So for search, we just need to remember this extra step, which is when we search for something, see if that spot's in use. If it's not, we're done. If it is, see if the key matches. If it does, we're done, we found our data. If not, we need to rehash. Everybody clear on that? Alright, so deletion gets a little more interesting. Let's say we want to delete K2. So how do we remove K2 from our hash? How do we make it so that if you search for K2, your code will come back and say, nope, that's not in the table? Set the valid to 0. So if we clear out this valid or in use bit, now when we search for K2, it's going to hash to this location, but we're going to check the in use flag. It's not set. We're going to say, oh, K2 is not in the table. All right, there's a wrinkle in here. There's a problem that we've introduced. So who sees a problem? Not checking all the in-use nodes. Let's see. Is what not checking all the in-use nodes? So first of all, just to be clear, my valid and in-use, I'm treating those as the same, just a different name. So to delete, really all we need to know is you know, we need to find the key. And yeah, if we say it's not in use anymore, now if we search for K2, it'll map, but it won't see it as valid, and it'll say, nope, it's not in the table. But we've set up an issue that will kick in down the road. I'll tell you in a minute if you don't come up with it. Memory leaks is a possibility, but no, not in this case, because we're still not doing any dynamic memory yet. Oh, so if we, you know, had allocated space for the key and the data pair, then yes, we absolutely need to free that memory, as well as marking the valid as a 0. So yeah, there is a potential for memory leaks here, and we need to take care of that. There's a problem with the hash table, though. So suppose I try to fetch K4 now. What's the first thing that's going to happen? We fetched K4 a minute ago and it worked fine. It's going to look for where it was. Okay, so how do we look for K4? We hash that key with a probe of 0, right? And what location does that give us? That says, oh, it should be stored right here. We look here and we say, is there something stored here? No. We're going to give up and say, I guess K4 is not in the table. So you see the problem here? Yeah, it won't find K4. K4 is not stored here because when we tried to store it, there was something here that caused a collision, and so we rehashed and we stored K4 down here. But now if we go back and we look for K4 and we don't see something stored here, we don't know that there was a collision that happened when we stored it. We just see, hey, this spot's open, K4 is not there, I guess it's not in the table. Okay, yeah, so that's what you meant by not checking all the in-use nodes. All right, so how do we deal with this? We don't really want to go through the whole table and for every node that's in use, see if the key is equal to K4. That's going back, to last week when we were just searching an array. So we have to embellish our structure. We have to add one more flag, which is a deleted or was in use flag. So here's what our whole structure will look like now. I never leave space for headings. So here's our key. Here's our value. Here's our in use. Here's our deleted. So all the in-use flags start off at 0. All the deleted flags start off at 0. That's not strictly necessary, but just to make it cleaner. All right, so store key 2. So let's say key 2 hashes to here. So we're going to store K2. We're going to store a value 2. We're going to say that's in use. When we hash key 4, it unfortunately goes to the same location. We see that that spot's in use, so we rehash. And now it brings us, say, down here. That spot's not in use, so we store K4, we store value 4, and we say it's in use. So far, same as yesterday. Okay, now we delete K2. So we hash K2, it comes over here, we check the key, that is K2, so we delete. We set the in use to 0, but we set the deleted flag to 1. Now if we try to find K4 in our table, what do? We hash K4 with a probe of 0, that takes us to this location. The in use is 0, so we know that what we find here is not valid. Right? This is not an entry for key 2. But we also check the deleted flag. And since there was something in here, right, which the deleted flag tells us by being set, we have to rehash. So we'll go ahead and we'll rehash with a value of 1, which brings us down here. We check the key, we check it's in use, we check the key, that's K4. There's our value that we fetch. So that's the last major complication on algorithms for hashes with this approach. So questions about that, and then let's write out these algorithms. So we could set deleted back to 0 when we use a node. So let's say we store K5, and let's say that maps over to here. So we would store K5, we'd store value 5, we would say it's in use. You could go ahead and set the deleted back to 0 just to be clear, but if we look at the algorithms we're about to write out, it turns out if a node's in use, we're going to assume it's not deleted, right? So we would have something like this. If we made a truth table, because that's what we do. So if in use is 0 and deleted is 0, this is never used. If in use is 0 and deleted is 1, then we had a node in there before, but it's been deleted. So if we bump into that, treat it as a collision. If in use is 1 and deleted is 0, or in use is 1 and deleted is 1, both of these mean, you know, the node is in use. The only advantage to setting the deleted back to 0 or not setting it back to 0, if we don't set it back to 0, then we know that this node is in use, but it had something that was deleted. And so this is at least the second time we've used it. Whereas this would be the pristine state where it's in use for the first time. So if for some reason we wanted to keep track of whether something had been deleted from here, we could leave the deleted flag to a 1, or we can set it back to 0. But there's really only 3 conditions we care about. Is the node in use? Is it not in use? Or is it not in use because nothing was ever stored there, or is it not in use because something was deleted? So I'm just going to go ahead and set deleted back to 0 just to make it a little less confusing. All right, other questions, thoughts? All right, so let's write some pseudocode. I'm just going to go with put and get. So let's put key value into our table. So initialize our probe, counter to 0. So hash table, bracket, so hash our key with our current probe, use that as an index into our hash table. And while that's in use, see if we've done too many tries. Otherwise, just bump up the probe and rehash. So hash our key with a probe of 0, see if that entry in the hash table has an in-use flag set. If it does, bump up the probe, try again. If that's in use, bump up the probe, try again. Right? Anytime in use is a 1, we know that spot is in use. And we don't really need to know what the deleted flag is. So keep doing this and have some kind of you know, exit point here if you've tried too many times. Once we come out of this loop, we have a spot in the table that's not in use. So copy key and value. Set in use equal to 1. And let's clear the deleted flag just for kicks. Alright, that's our store. Deleting a key. So hash your key. Using a current probe value, starts off at 0. make sure it's in use, and let's see. Let me do this cleaner. Alright, hash your key with the probe value. Use that as an index into your hash table. Check the in-use flag. Okay, if that in-use flag is not set, if that flag is set, and if that is set and the key is not equal to the key that you're looking for, then we need to rehash. Alright, so make your first hash attempt, find an index. If that is in use, but the key doesn't match what we're after, then we need to hash again. If this is not in use, but the flag was deleted, then we also need to go on. All right, so let me go more pseudo. Okay, so hash your key with your probe. If at that location in the hash table the entry is in use and the key is equal to the key, then we want to go ahead and delete it. So set the in use to 0, set the deleted to 1. And we're done. All right, if the table entry is in use and the key is not equal to the key we're looking for, increment the probe and go back and try again. If we get down here, the node is marked as not in use. If it's not in use, but it's marked as deleted, increment the probe, go back and try again. So I'm skipping all of the, check the hash table at the entry index given by the hash function, etc. business. That's what these brackets are. All right, so hash your key. Look in the hash table. If it's in use and the key matches, you're done. That's the node to delete. Set the deleted flag, clear the in use flag, get out of there. If it's marked as in use but the key does not match what you're after, rehash. Bump up your probe, go back, try again. If, when you look at that location, it's not in use, but it's marked as deleted, then you have to rehash. So bump up the probe, try again. Otherwise, it's not in the table. Right? The only way you get here is if in use is clear and deleted is clear. Let's see, chat. So if it's in use or deleted and not equal to the key we're looking for. Yeah, so if it's in use and not the key, or if it's deleted and not the key, we want to bump up the probe and rehash. If it's not in use and it's not deleted, then it's not found in the table. And if it's in use and it does match the key, then we want to go ahead and delete it. All right, and fetch is exactly the same thing. So get key. Well, it's exactly the same thing, except that when we find the key, we don't delete it. We just go ahead and return the value associated with it. All right, so this is squiggly, right? But the idea is relatively, it's a small modification on what we were doing before. The only modification is when you delete, you make a note that you deleted. And now when you're searching, finding an in use of 0 doesn't tell you that you're done searching. Check to see if it's deleted. And if it is, then go ahead and keep probing. But if you're searching for a key and you get to a spot where the key matches but it's not marked as in use, you can't say that's the key that I'm looking for. Right? It happens to have the same key value, but it's not actually part of the hash anymore. But this complicates kind of the picture of you know, where things go in your hash. Now, if you had a node that was deleted and you know, in use is cleared, deleted is set, and something else hashes to that location that you're trying to store, right? We'll reuse that location. It's still reusable. And once we do that, if we search for something, right, we'll notice that that spot's in use. That'll kick us on to reprobe. But the deleted flag is really used when this spot is temporarily empty to tell us that we still have to keep searching. All right, questions about that? So printing is pretty straightforward. Right, if you want to print the contents of a hash table, what do? You basically start at the beginning of your hash array, make a loop to go through each element, and for each element in your array, if it's in use, right, and, you know, presumably not deleted, go ahead, print out the key value pair. If the goal of your print function is just to print. So that you can do just by kind of going through from the beginning to the end of the table. But what can we say about the order in which the key value pairs will be printed if we do that? How does that order relate to the order in which we added them to the table? kind of random, right? There's no obvious relationship. And if you look, when we get to Java, we talk about hash maps. If you look at the methods for pulling things out of a hash table, it always says in no particular order, right? I mean, there is an order, but it really has nothing to do with anything. It's going to be, just kind of wherever these things ended up getting mapped to. So yeah, depending on how they were hashed. So that's kind of strange, right? But sort of cool. So if we just want to make a function that says, hey, let's just, take the contents of the hash and print it out in this particular format, we can write a print function to do that. And, for a programming assignment in this course, that would probably be sufficient. But for a genuine hash package that's going to be used by lots of different people, you don't know what format they want the stuff printed in. You don't even know if they want to print it. Maybe they want to go through, read the contents of the hash, and turn it into a linked list. And they don't want anything printed at all, right? Usually we're really, really cautious about printing from functions that we write, right? If you're writing a function purely for yourself, you can go ahead and print anything you want anywhere that you like. But if you're implementing a set of code that's going to be used by someone else, almost never are we going to do a print from inside there. So I noticed on PA2, for example, a lot of people's delete functions had print statements in there. That's not something we would want, right? Unless the description of the delete function says, if the node is not found, this function will print an error message to standard out. Okay, then you're good. But in general, that's not something we want. So just like fgets, if you hit the end of the file, it doesn't say you've reached the end of the file. It returns a code to you so that the person who called fgets can choose whether or not to print something. So same thing with traversing our hash. We don't usually want to just print. So this brings up the idea of an iterator, possibly spelled correctly. So what's an iterator work like? It works like something that hands you elements from a data structure one at a time. So this is usually a pair of functions. So this would be in the interface, right? Back to a hash as an abstract data type. This would be in our interface that a main program would use. So we could do something like start iterator, and then key equals next iterator. And maybe an iterator done function. So yeah, like a for loop. So this would probably be more like a while. So here's what we could do from our main program. So let's say we want to print the contents of the hash. The person said P right on their command line interface. So what we do is we say start iterator. And while the iterator is not done, this function tells us there's more stuff we haven't seen yet. So we could say key equals the next key from the iterator. And then value could be something like, fetch key. And then we could print those out. go back up to the top of our loop. So what does this do? This initializes something inside our hash code to say, hey, when I say next iterator, give me, the first key in our hash, right? Where first isn't necessarily, the one up here, but give us a key from our hash, right? And this tells us, is there anything else that we haven't gotten? In other words, if we call next iterator, will we get a key we haven't seen yet? So as long as that's the case, go ahead, give me another key, fetch the value associated with that, print those out, go back up. Have we gone through every key yet? If not, get another key, fetch the corresponding value, print those out. Right? These are really easy to use. They're a little harder to implement, but pretty straightforward to use. And if we wanted to break that firewall that makes this an abstract data type, right? Our main program could make a loop which said, for I equals 0 to 30, if in use is 1, print out the key and value. You never want to do that though, right? How does the main program know that this is 31 characters long? How does it know about the in-use flag and what the in-use flag means? How does it even know what the key and value are called in this array, right? For the main program to work with this directly, we need to expose all kinds of internal details about the implementation of this hash. And now your main program is critically dependent on this particular implementation, and if I link that main program with somebody else's code, it's probably not going to work. So if you have, part of your interface is this facility for handing you keys one at a time, right? Now we can successfully have a main program that goes through and prints or does whatever it wants with the key value pairs. If I didn't want to print, I could make a new node containing that key and that value and add it onto a linked list I'm building. So think about how you would go about writing an iterator, and I'll probably spin up an ODP that uses iterators in some way somewhere in the next few weeks. But that's a concept we'll come back to, and we'll play with this more with other data structures. Alright, so think about that. That's a pretty good synopsis of hashes. I will probably try and get your next programming assignment posted sometime today, and then we can talk about that tomorrow. Alright, have a good one. See you next time. Thanks. You're welcome.